Welcome everyone to our to the final day of the QSC Quantum Summer School. Today we have very exciting program. And today we will have a workshop from Microsoft and also three lectures followed by panel discussions with speakers from previous days and from today's sessions. With the morning session, we will start with introduction, the second part actually of introduction to Q# and Microsoft Quantum Development Kit. And I'm very happy to introduce our speaker, Mathias Soeken, who is a senior software engineer from Microsoft. My name is Alexander Senichev. I'm postdoc at Purdue, and I will moderate this session. If you have any questions, please type them into Zoom chat and on YouTube. And without any further ado, Mathias, the floor is yours.
Yes, thank you very much. It's a pleasure for me to speak here today about Q# and the Microsoft Quantum Development Kit. I'm Mathias, and I'm the senior software engineer with Microsoft in the QDK team. And I'm working with Q# to develop quantum algorithms. And today in the second part of the introduction to Q# and the QDK, I want to show how to use this framework, to language, and the ecosystem that comes with it to develop large-scale quantum algorithms and show a workflow that helps you building these applications. Of course, in this limited amount of time, we will not build a large application, but I show in a small application what kind of decisions we can take, what kind of tools we can use, and I think it will give the idea of how this will scale up for large applications. So this is the flow of a quantum algorithm in this workflow that I'm describing today. Initially, we have some quantum algorithm that we wish to implement. This could be given in any kind of form, very informal, for example, right? So this could be like a description in some textbook or some paper that describes how the algorithm works and how it makes use of quantum mechanical effects. Now we wish to have a formal implementation of this algorithm so that we can automatize things around this algorithm. And we suggest to implement this algorithm inside the QDK in the Q# programming language. So we would express the algorithm and implement it as a Q# program. That would be our single source of truth that describes the algorithm and on which we will be our starting point for all kind of different tasks that we want to do to analyze this algorithm. And this analysis of the algorithm happens in this test phase, which is this third phase. Also, they're kind of tightly interleaved with each other. And what can we do in this test phase? We may verify the program, right? We want to make sure that what we implemented is correct. Does it implement the right functionality? We may want to debug the program, and one good way to debug a quantum algorithm could be visualization. So how do the different quantum operations interact with each other? And then we want to do something with the algorithm for some purpose. So we may, for example, run it on hardware. But what we can also do is we can estimate the resources. What does it mean? So I want to understand the implementation of my algorithm. How much will it cost? How much operations will it require? How much qubits will it require? And there may be different ways to implement the same algorithm leading to different resource estimates. And I'm interested in having good resource estimates, because the resource estimates will also tell me how long will it take to run a quantum algorithm on a quantum computer? What kind of size of a quantum computer will I need to run this algorithm? Maybe now or maybe in the future. And another step that is in between is, for example, I could rewrite this algorithm. And I'm not talking much about this step, or I'm not talking about this step today, but just to emphasize that it can be part of the flow in which I implement my algorithm, but then I can optimize this algorithm based on the program itself. So if I have a program, I can run different optimization steps that happen, and then I will verify that the optimizations are still correct with respect to my initial program, or perform my resource estimates on the optimizations. So please feel free to ask questions at any time, and I can take some questions in between if there are questions about the content I'm talking about. So today I focus on doing resource estimation, but similar things apply if I run my algorithm on quantum hardware. It would just be another arrow to take the same program. The important thing is that it's one program and then multiple uses of this program. I want to show an example of this flow, and I'm going to show some code and how this can be implemented in Q#. And as running examples through this demonstration, I'm going to make use of this majority of 3 Boolean function. This is a function that takes as input 3 variables. This is like just a notation with these angular brackets. And the inputs are 3 Boolean variables. So each of these variables can be either 0 or 1. And this function evaluates the true if the majority of these inputs is true. That's why the name. And there are 3 variables. So if 2 or 3 of these are 1, so the sum is greater than 2, greater than or equal to 2, then this function is 1, and otherwise this function is 0. And we wish to implement this function inside a quantum program. So why are we interested in doing this? It seems to be a very simple function. It's not even a quantum function. It's a classical function that takes Boolean inputs. But the reason is that these classical functions are often used in quantum algorithms. They're sometimes also called oracles. For example, in a Grover search, we have a Boolean function as input, and that represents the data that we're like searching, and that is encoded as a classical Boolean function. Or in Shor's algorithm, we, for example, take arithmetic functions, exponentiation, multiplication, and others as arithmetic functions that are classical functions inside the quantum algorithm. The difference is only that the input to these operations will be quantum states. So instead of assigning like a concrete value to x1, x2, and x3, these input variables can be in superposition. But it's completely fine to consider this function classically and exercise all concrete value assignments for x1, x2, and x3. This is because quantum computation and quantum operations are linear, so it's fine to just make sure that this function is correctly implemented on the linear set. But we get to that. However, if we want to run it integrated into our quantum algorithm, and we want to make sure that it can take quantum state as input, then we have to implement it in terms of quantum operations. So we cannot use classical logic to implement this function. So we need to use quantum operations. So now how do we implement such a function? And that heavily depends on how I represent this function. So as I already said, that the task is to implement this operation such that we map. And concretely, what we want to actually implement is we have 4 inputs, 3 qubits that represent the input state of the function, and 1 qubit that represents the output state, y. And then we want to invert y whenever the function evaluates to true. Right? And if you would assign y to be a clean qubit in state 0, then the qubit afterwards will be exactly the value of the Boolean function. So it depends. We can implement it if we have a representation for this function. And here's one simple representation that we can always do for a Boolean function that is explicitly enumerating all the possible input combinations that we can assign to this function. Here we have 3 variables, x1, x2, x3. So these are like 8 possible different input combinations, assigning each variable to 0 or 1. So for small Boolean functions like this with a few number of inputs, this is feasible. But if we have, of course, a large Boolean function, then this is not feasible anymore. So we explicitly enumerate all the input assignments and then say when f is 0 and f is 1. So we see in all these rows in which we have more than 1, 1, f is 1, and otherwise it's 0. I'm also having a column called I, which is just the index of that row. And as index, I take the decimal representation of this bit string in which x1 is the least significant bit and x3 is the most significant bit. For example, 011 is the binary representation of the decimal number 3, whereas 110 is a representation for 6. So let's take a look how we could implement this function in Q#. I created a project, and I did this project in VS Code. So there is multiple different ways to execute Q#. We could do it in Visual Studio, VS Code on the terminal. You can do it in a Jupyter notebook with IQ#. I decided to use VS Code for this purpose and using a .NET project. So there's a file that is a solution that combines different projects. And the first focus should be on this project, which is in this folder library, which is a C# or like a Q# project for a Q# library. So in this library, we can implement different operations, and then we can write later a test suite or a program to call these operations from the library. The idea is that we have a library that we can reuse and use among different kind of projects, for example. So in this library, I have different operations implemented, and let's focus on the first implementation. The first operation here, which is called apply majority from ints. Let's go back to the truth table. What I want to do is I want to make use of this fact here that I know f is a 1 whenever this row has index 3, 5, 6, or 7. And what does it mean if it's 1? If it's 1, it inverts the value of the output qubit. So here is my signature of this operation. I'm having a namespace, and I use different namespaces here. We'll get to that, what these offer to us. They're coming from the Q# libraries, standard libraries that are shipped together with the QDK. So this operation is called apply majority from ints. So it's one variant to apply this majority operation based on these integer indexes in the truth table. This signature is it takes 4 qubits, A, B, C, and F, where A, B, and C are the input qubits and F is the output qubit. What I did here to kind of like emphasize that A, B, C are input qubits, I grouped them as a tuple. This is like something I can decide. I could have also not using these parentheses, and it would be a function of like 4 inputs. Now it's technically a function of 2 inputs, one 3-qubit tuple and one single qubit. I could have also decided to let these inputs be a qubit array. But for my signature, I decided that I would like to have these inputs as a 3-tuple and the output as a single qubit. This operation does not return anything. It doesn't return a qubit. It takes this output qubit and modifies its state. And this function is adjointable and controllable. And we don't have to specify anything because to get them adjointable and controllable, the Q# compiler will automatically understand how to invert this operation if I want to call it in an invertible way, or which operations I need to control if I would like to control these operations on another set of control qubits. So how is this implemented? In order to implement this, we use this function apply controlled on int. And that's a library function. So these come together with the Q# standard libraries, and you can find them all in the Q# documentation. So if you go to the API reference, and there's the Q# libraries, and then they're all in here. And this particular one, we can also search for it, apply controlled on int, is in the Microsoft Quantum Canon namespace. And then it has this signature, so we can check what this is doing. It we can read it. So it's an operation that takes as input a number state, where this is a number on which we want to perform some operation. Then it performs some generic operation that takes as input some generic argument, type argument t. It has some control register, which is the qubit array, and then some target register on which I apply this operation, which is this generic argument t. So I'm applying this controller integer on all the possible inputs that turn the function to be 1. That was like 3, 5, 6, and 7. And what do I want to do? I want to apply an X operation, which is exactly inverting the output qubit F whenever these controls are in this input state input. Right? X is an operation that takes qubit as input, and that determines now what is the generic argument of our operation, and F is also of type qubit, so these two fit with each other. If we would, for example, apply another operation here, we could apply, I don't know, a CNOT operation that takes 2 qubits. Well, then we would have to provide a 2 qubit tuple here, for example, AB, which is of course not implementing our function now, but so it's a generic operation that matches this operation that we apply together with the target operation, target register that we apply. Are there any questions so far?
No, we don't have any questions so far,
Okay.
but I will let you know once we have one.
Sure, perfect. Thank you very much. Okay, let's see other ways how we could implement this operation. We could also rewrite this function as a Boolean expression. So if we maybe sit down with pen and paper and use some of the Boolean algebraic rules that we know, we can maybe find that this function f evaluates with this expression. So what does this expression mean? It's like x1 and x2, XOR x1 and x3, XOR x2 and x3. So when we can quickly see that if none of the input variables is true, then none of these terms evaluates to 1, so they stay 0. And similarly, if only one of the inputs is true, none of these AND terms can be true, so the function is 0. So that's good. We can also see if exactly 2 inputs are true, then only exactly one of these AND terms will be 1, and the function will be evaluate to 1, which is also what we want. And if it's 3 of them are true, so all inputs are true, then all these terms will evaluate to 1, and then we have the property that 1 XOR 1, XOR 1 again, is also 1. So an odd number of variables in this XOR expression is 1. So this is also a way to express a Boolean function for majority, but using a different way. So we see here that if we now think about this term here, we invert the output qubit y when f is true. Now, if we would substitute y using this expression over here, then we can see that we invert y if an x1 and x2 is true, and we invert it again if x1, x3 is true, and we invert it again if x2 and x3 is true. So it's somehow like applying 3 different functions onto this output qubit y, each function corresponding to one of these terms. And that we can express using a Toffoli gate or controlled NOT gate. That is a NOT gate controlled on 2 input qubits. And this implementation right here is using this property. The signature did not change, just the name of this operation changes because we want to distinguish it from the other one. It's now called apply majority from CC NOTs. The CC NOT is like controlled NOT. And then we invert this function for every of these input terms. So if A and B is true, we invert F. If A and C is true, we invert F. And if B and C is true, we invert F. And if you think about this way how we describe that F is a valid Boolean expression for this operation, then we can kind of see that this should work. Right? If only one of these inputs is true, none of these gates will be executed. But if exactly 2 is true, one of these gates will be executed inverting f, and if all three of them is true, all CC naughts will be executed, also changing the value of f. We can also, so this was looking at the expression. We can also go back to the truth table and use some other functions that are provided by the standard library. So if we know the truth table value, so if it's not too, as I said, not too many variables, then we can write down the truth table. Then we can also call a function provided by the Q# libraries inside the synthesis namespace that is called apply x controlled on truth table. So it's really applying the x, like inverting some output based on the value, based on the truth table as input. So we can explicitly say the truth table is this number. And how do I get this number? Well, a truth table, we can also think of it as a number. But if you like, a table is always like, a truth table is always written as a table, but what really only matters is whatever's in this column. The other values in the other rows, sorry, and the other columns are always determined based on the number of inputs that we have. Right? This is like always enumerating all the assignments. So the only change in a truth table is like what happens in this column. And we can think of this as a long binary number with the most significant bit down here and the least significant bit down here. So 1, 1, 1, 0, 1, 0, 0, 0. This is like some 8-digit binary number that has some decimal representation. And we can write down this number directly here. And because we have it given in binary, we would like to write it in binary. So we prefix this number with 0b, and then we can write down all the bits. We suffix the number with an L because the type of this number is a big integer. That guarantees us to write long truth tables, which have more than 64 digits, which is the maximum digits for a normal integer that corresponds to a 64-bit value. So the truth table is the first argument. Then we can provide a control array. And I missed to say it here. The input argument is a qubit array. So we take our single input qubits and put them into an array to call this with this function and apply it to our output qubit f. So that's the third implementation of the same function. Now we can try to find better expressions or better implement maybe different expressions for the same function. And a rule of thumb is to reduce kind of like the costs of a quantum operation. And we talk a bit later what I mean with cost is to reduce the number of AND operations in the function and have more XOR operations in the function, as they turn out to be a bit cheaper when implementing on the quantum computer. So with a bit of like manipulation of this function, we can also see maybe that f can be written in this form. And it's easier to kind of like validate that this is true. So what I'm having here is two XOR terms ANDed together and one more XOR term. So let's take a look at this first part over here. What does it evaluate to? Well, it first takes x1 and x2, which is one term of the sum, which we get over here. It takes x1, x3, which is this term over here. It has x2, x3, which is this term over here. So it already produces all the terms of f that we have written up here, but it also produces the term x2 by ANDing x2 with xAND. Sorry, with ANDing x2 with itself. So it is this conjunction creates f as we have it here, but also another XOR x2. And to remove this other XOR x2, we just XOR x2 one more time, because then it cancels this extra x2. So and therefore it should also be the same as the majority of 3 function. And this is then implemented in this last operation here. Again, the same signature, but a different name, apply majority from expression. And what we're doing here is we first, so what do we need to do? We want to compute x1, x2, and x2, x3, and then AND these together. So I could now compute x1, x2 on maybe some temporary qubit. But what I'm doing instead is like I compute the result of x2, XOR x1 onto x1. So I compute I compute a C0 from B to A. Therefore, like after I apply this operation, qubit A will now contain the sum A XOR B. And similarly, after applying this operation, C will contain C XOR B. So now A and C are not available anymore directly, but they contain the value of like A XOR B and C XOR B, which is exactly these two terms. And then I want to like take the AND of these two and invert the output qubit if that is true, right? This is like this first term over here. Just now it's not like this single literals, but it's like the XOR terms that I have temporarily computed onto x1 and x3. So we can ignore this with and apply for a moment, and then I explain later what it means. So we can just read these instructions. Then we take the value of A and C, which now contain set the XORs of A XOR B and C XOR B, and apply it to F. And then we apply also XOR B, so this last term over here, onto the output qubit. But now our qubits A and C have been modified to contain the sums that we needed here. So we have to uncompute them again to bring them back into the original state, because our operation should only modify the output qubit, but leave our input qubits in the same classical state. And we do this by taking basically these operations and apply them in reverse order. And because this is such a common pattern, there is a dedicated syntax construct in Q# that does that for you, and which is this within apply construction. So within this computation, apply that computation, and when this is done, we apply these operations in inverse afterwards. So we don't have to like repeat ourselves. Here's just two instructions, but this may be like a more complex code, and then it really helps. Even for these two instructions, it helps to kind of provide more intent to the code of like what is this doing. So now our library has 4 different implementations of the same operation. So that we do this because we want to check what is a good implementation of that, what is the operation that we favor, and that we're going to do with resource estimation. But before we estimate resources, we first want to make sure that these operations in fact implement the majority function. And for this purpose, I have implemented a test project in Q#. And before we go there, I want to like first highlight some of these properties or like capabilities of the quantum development kit. So we can now, as I said in this beginning picture, like exercise and run this program for different possible tasks. And these are called simulators in the quantum development kit. So a simulator is something that executes your quantum program. So your quantum program in the end is like a collection. It is a procedural description of when to apply quantum operations to qubits. We can use high-level library functions and functionality, but in the end, it always boils down to elementary operations that can be performed on the quantum hardware. For example, an X operation, a C0 operation, a CC0 operation, and so on. So these simulators assign semantics or meaning to these intrinsic elementary operations. So what do I want to do with them? And one thing I can do, for example, one thing I can do for sure, and is not mentioned here, is run them on quantum hardware. That's a probably like most interesting purpose to run a quantum program. But what you can also do, you can like simulate your quantum program. Right? So we can, for example, have a full state simulator that now, instead of like whenever it keeps track of your quantum state in memory, and whenever you encounter an operation that is executed, so while we execute the program, when we apply an operation, we modify this quantum state in memory. And that is like performing a full state, precise simulation of the quantum operation. And that is limited to the number of qubits. Huh? If not, then we would not need a quantum computer, right? Because we can only like simulate it, and to simulate a quantum computer, we need to express the quantum state, which takes exponential space. So this would work typically for like maybe up to 30 qubits on a laptop, depending on what laptop you have. But for a small number of qubits, we can do this full state simulation. Then there is a Toffoli simulator, which is a restricted simulator that also can simulate some quantum algorithms, but it's limited to only what is called, like, let's say, classical operations. So it will not represent the full quantum state, but it will represent the binary input assignment of the current state. So this does not work when you have states in superposition, but for classical operation, it works. So as long as one only applies X gates, C0 gates, multiple controlled X operations, and so on, then this works fine, because it only needs to assign one Boolean value to every qubit. And that's why it works for like many qubits. But if you need superposition, so for example, using a Hadamard gate to introduce some superposition, then this will not work. And also other tasks can be thought of in this framework, which is just like running the program and doing something when we encounter elementary operations. So for example, resource estimation is just another way of like describing a simulator. That means that whenever we see a elementary quantum operation, then we increase some counter for this operation of like how often we have seen that. Or whenever we allocate qubits, we increase one counter for like the number of qubits we use. Or we deallocate a qubit, we decrement this counter. So resource estimation is like, in the same sense, like a similar backend to the full state simulator and Toffoli simulator, but just doing something different while running this quantum program. And that's going back to the beginning. It's like you write your program once, but you can do different tasks with it. More extensive resources estimator in the QDK is called the QC, trace simulator. That does also resource estimation, but collects many more information, not only like a counter to the individual operations, but it also like can track the whole call graph of the algorithm, like in which sub operations have you visited, in which order, so we can get the tree of like what operations have been visited, how deep does it go, and so on, and can be customized to how to count operations and giving them weights and so on. And this whole simulation framework is entirely customizable. So we can write custom simulators and decide what to do when we encounter these operations, and have our own ideas. I would refer you to the Q# blog, which has a blog post series about how to write custom simulators. And I will also highlight one of these custom simulators soon in the talk. So we use now the simulators to run our program. And one way, there are two ways to run if you do it locally on your computer using the .NET framework, then there are two different project types that allow you to execute code. One is an executable project, like a command line tool, for example, and the other one is a test project. And I created a test project that refers, so this is a test project that has been created with a template that is shipped with the Quantum Development Kit extensions. And it refers to this library project that I have, that we have looked at. And now it implements some tests to check whether the functionality is true. So we can just write, and it uses also Q# as a language. We can write operations that take no input and have no output, and decorate them with this test attribute. And the test attribute then is assigned a simulator, like TOEFL simulator, full seat simulator, that is used to execute the code in this test case. So I have like written 4 different tests for each of the 4 different implementations of the majority, and there's like a function verify majority that I used as a generic function that I can pass all these different implementations. So how, and it is implemented in this test project. So how does it look like? We have this operation verify majority, which is declared internal, as it's not used outside of this project. And it takes as input one input called match. And this is of type this. So what does that mean? The type of this argument match is itself an operation. So just as integers or strings and booleans are types, an operation or a function can also be a type. And this is indicated by, for an operation, by this double stroke arrow. It has on the left-hand side the signature of this operation, on the right-hand side the output type. So the signature of a majority operation was 2 input arguments, 1 3-tuple qubit and 1 output qubit. And it returns nothing, so it's unit, and it's both adjointable and controllable. So we just took the same signature, and that's why it was like convenient to have both all operations with the same signature, because now we can reuse this code. And this was like qubit, 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 tuple, another qubit, 2 unit being adjoint and controllable. So there's one argument to our function verify majority, and then how is this function, sorry, this operation implemented? We allocate now some qubits because we want to execute this operation, and we allocate 3 qubits for the input A, B, C, and 1 qubit for the output. I might have as well used the same lines as I did here for, like, for example, A, B, and so on to allocate these qubits. I just decided to do it like this as a tuple syntax to kind of emphasize that these 3 qubits belong somehow together, because there's the input qubits and this F is the output qubit. But this is completely up to you when you write these operations. The use is a keyword that indicates that we allocate a new qubit, or let is a keyword that indicates that we create some variable. And I'm creating now a variable array, an array of these 3 qubits. So this is not a new array of new qubits, it's just the existing qubits we have, just represented as an array combined together, because I need them in some operations in this code. Now to verify them, I assign all possible input combinations to my input qubits, and then run the operation and check what is the output for this operation. Sorry, what is the output for this input assignment? So we go for all these input assignments by just using the index of this integer. So like we had this first column, which is an integer from 0 to 7. And in order, now I have my input qubits that are in state 0, and I have to assign my input qubits to to a state that corresponds to my input state I. And I do this by using this operation, apply Pauli from bit string. So this is a more generic operation. It can do more things. We can take a look what it does in the documentation. So it applies some Pauli operator, and Pauli X is an operator that does an X. So it's good with what we want, like to a qubit array, if some corresponding Boolean array matches this input. So we apply an operation like, for example, X. If this qubits to each of this qubit corresponding to this values in this array, which is of the same length. And we apply this operation if corresponding to this value. So what I want to do is, like, when this value in this bits is true, then I want to apply this Pauli X to the controls, A, B, C. And how do I get this bits? By just like taking the integer index 0 to 7 and representing them as a array of Boolean values of length 3. Taking this value and then say, give me 3 Boolean values, like a binary representation as a bit string of length 3 that represents this value. And this essentially, if you go back here, takes this index I and returns me this input assignments in these 3 columns in the middle. So now my input qubits are assigned to this corresponding input index state, I. And now I apply the majority operation that has been passed as an argument to this operation to these 3 input qubits that have the state onto the output qubit F, which is in state 0. Right? Whenever we initialize the qubit is in state 0. And now I measure this qubit in Z basis. So I just measure if it's 0 or 1. And this operation M reset Z is measuring it and also resetting it back to 0. So we want to like take the same qubits and iterating in this loop and always assume, like, as an invariant that the qubits at the beginning of each loop are 0. And then this function returns as output. We can hover over this function operation and then see what is a synopsis. It returns a result value. A result in Q# is a specific type to indicate a measurement result. This is either 1 or 0. And we convert it into a Boolean value by using this function isResult1 that takes as input a result value and returns a Boolean value. So now actual is either true or false, depending on the function inputs. And the expected value should be true if the index is either 3, 5, 6, or 7. And since we iterate I only up to 7, I can just ask, is I equals to 3 or is I greater or equal to 5? And then I want to check if these two are equal. I could just do an if expression. But again, I can use library functionality to express intent. And there is a diagnostic namespace that has a lot of these operations to express assertions. And this particular one checks if 2 Boolean values are the same. And if they're not the same, then I can report some error message that will be printed by the test. And this function ensures that it's like nicely formatted, and it also gives me the values of this function in some extra output string produced by this operation. And all these operations and functions being used are taken again from the quantum Q# libraries, and they are like categorized in different namespaces. So, for example, conversion functions like this are in the convert namespace. And if you want to see, for example, more of these, then you can in the documentation you find all the namespaces, and you can have a page which lists a summary of this whole namespace, and you can see then there are many more functions. We had this one over here, int as bool array, but there's also double a string and bool a string, or yeah, and others that take a type and convert it to a different type. So then now we have this generic implementation to verify an arbitrary majority operation that takes this signature. And so we can apply this to all these operations, right? One test case for each of these different implementations. And then we can test this project. So if I call .NET test in this folder, it tests all the test projects that are in this solution file, and there's only one test project in this solution file. So I compile the project and runs the project. And then we hope that all tests pass. Well, it ran all the tests. There are 9, but these 9, and we look at the other 5, but these 9 includes this 4 that we just discussed, and they pass. So that exhaustively tested all the operations that we have. Now let's take another look at the signatures for the tests. We're using Toffoli simulator for all these tests, right? Because we are only enumerating all these classical Boolean assignments and running them through the operation, and then checking if this is true. But we're using quantum simulator here. So the reason is that this operation, truth table operation that we have over here, apply majority from truth table, is not implemented using classical operations. So it uses quantum operations in the implementation of that truth table. And therefore we have to use a quantum simulator for that. But if we would try differently, then we would it would not compile, or it would compile, but it would fail executing it because there is an operation that it cannot simulate. Let's just take a look at that. So we see that here that now, in fact, actually, this Hadamard operation that is part in the implementation of this way to implement the operation cannot be executed on a Toffoli simulator. And that's why we have the quantum simulator here. All right, so that's one way to implement these operations, and that's very like yeah, it's a good way if you can exhaustively enumerate all the combinations for a classical operation. But there are alternative ways to do that, and there are more generic ways. And these are particularly useful for also like other unitary operations where you don't have like this maybe enumerating all the classical values so easily. In the diagnostic namespace, there is a function that is called assert operations equal referenced. So that it's asserting that 2 operations are equal, and this reference is just like a hint on how this is implemented using some reference qubits. But we don't have to bother about this in this part. So let's take a look how this operation is defined. So this operation takes a number of qubits and then has 2 operations, actual and expected. So expected is our kind of like reference implementation that we want to, like we know expected that this should be correct. We have some kind of way to have that shown that the expected is correct, and actual is now, let's say, our operation that we want to verify. Essentially, what this operation is doing, it performs a superposition on n qubits. Right? We have all the possible input combinations. It runs them through actual. It modifies the state, and then it calls this expected operation in inverse order. And we can see that here that this operation must be adjointable. So this must be invertible, this operation. The first one doesn't need to be. it calls the expected in inverse order, and then the output state should be again a superposition of an equal superposition of all the input combinations. So we undo this superposition in the same way as we created it, and then expect that our output state should be all 0. That's more or less what's going on in the implementation of this operation. So like this, we're not like having to enumerate all possible assignments. We use like superposition to actually do that for us. But the operation has to be defined in some, it is variable over the number of inputs, right? So if I have an operation that takes an arbitrary number of qubit inputs, I could check it for different sizes. We take 4 inputs, but we don't take it as an array. So this signature expects us to provide 2 operations that take as input a qubit array and return nothing. But our functions do not take as input a qubit array. It takes as input a tuple of inputs and a qubit for the output. So what we're doing here is we know the first variable should be 4. We have 4 qubits that our operation is applying to, but the signature does not match. So we write a helper function, a helper operation, apply majority from array, that takes our majority operation, that is again the variable in this majority signature, like we had before, and modifies it in a way that it's now an operation on qubit. So let's see what's happening here. So we write this operation apply majority from array. This is like a wrap operation. This takes 2 arguments. It takes 1 argument, the majority operation, with this, up to here, with this signature that we use for majority operations, a 3 qubit tuple for the input and a qubit for the output, and a qubit array. And it's just like some quantum operation. Now what we're doing is we take out the individual qubits of this qubit array. We expect them to be 4, so we can write an assertion that to make sure that this is 4. Extract these 3 qubits, A, B, C, and F, and then rearrange them such that they match to our signature from the majority operation, like putting the first 3 input qubits as a tuple and then the output qubit. So it's just an alternative way to call this, essentially, right? So we could, let's say, so if we hadn't done this, we could say, for example, use qubits. So we allocate 4 qubits, and then if you want to call this operation, say we call it apply majority from ints, right? This would be our operation. Oh, no, we don't have to do this majority operation, right? So this majority operation has a signature. Then we cannot call it on this qubits, right? This doesn't fit. It doesn't. We could try to extract these and then write them separately, but we cannot apply it to the array. But we can use this wrapper function to actually apply it by saying, okay, we just take the majority operation and then pass in the qubits. Now this would work, right? Because it takes its qubits, splits them up, and assigns them to its majority operation. So this is like a concrete instantiation of this operation and applying it, in fact. So it creates this operation. Sorry, it creates and calls this operation. In Q#, we have something that's called partial application. So we can create new operations from other operations by leaving some arguments empty. What do I mean with this? So this operation has some type. We can see it, for example, by storing it in some variable. So we take this operation, and this has some type that has these 2 inputs, right? This long signature for majority operations and a qubit array. But I can also like fix one of the inputs and leave another one empty by just discarding it using this underscore. This creates another operation. This doesn't execute this operation. It creates a new operation in which the first argument is fixed. So now this operation is of type qubit array to unit. And that matches this operation that we need to pass in this assert operations equal reference, which is a qubit array to unit. Well, we can ignore that this is now adjoint and controlled, so it's stronger. It's stronger than what is expected, so that's why it works. So if it's adjointable and controllable, it's also just adjointable. So we can call them like could also call it like this, like op1 and op2, which are like now modified operations based on this majority operation, but like they leave some argument empty. So now we kind of created new operations that perform majority one, but in a different signature. And so maybe this is a bit clearer than to write it like this. And then we have like this. It's just a wrapper to do this task. And like this, it allows me to reuse more generic functionality by writing some helper operations to match these signatures. And as a matter of fact, like here we have a very specific signature for this majority operation. But in the Canon namespace, there are a lot of operations that that do this for me. Like, for example, apply to first qubit. Right? If I have an operation that only takes one qubit and I want to apply it to a quantum array, I can use this operation and apply it to the first two qubits. I have an operation that assigns 2 qubits, that takes 2 qubits, but I want to pass in an array, then I can use these operations. And it becomes very powerful in the combination with partial application to create new operations. And then I can combine them and compose them into something. So now with this operation, I can, for example, write a test case like this, that now takes 2 of these operations and checks them for equivalence. And what I did here is like kind of like creating a cycle, or like not really a cycle, open-ended cycle. Like it compares ints with CC naughts, the CC naught implementation with the truth table implementation, the truth table with the one with the expression. So now I kind of like compared everything with it's a transitive chain to compare all these different implementations with each other. So now I'm kind of like confident, because we ran this test and this included this test as well. Now I'm confident that the operation, the majority operations, implements a majority function, and also that they're all the same. You could have, like, maybe in some more realistic example, you would have one verification that is somehow exhaustively in all the combinations that you know, okay, that adheres to some specification, right? Because the specification is like really inside this test case over here. And then this other operation, the equivalence check, is just checking if these two are the same. They don't check for the specific majority functionality. So if it could be that all the operations are equal to each other, but all are wrong. So it's kind of like a good mixture to have one test that compares with respect to a specification, and then one test case that then does this equivalence check, for example. All right, so now we would like to compare these operations. We write 4 different operations if we just want to apply majority. So there must be some difference in these operations, and they are like quality-wise. So in order to estimate them, I wrote a Q# console application as inside here. So it's like just an executable Q# program that has one Q# file. And I can call this from the command line. It has one operation that can take some input arguments, and this unit could also return something, in fact, and is marked as an entry point. So this is like in some languages, maybe like what you would call a main function. This is the one that you execute when you run the program. It can have any name as long as it's marked as entry point. I call it estimate resources for majority. And this should be a program that I can pass in a type of the operation, and to indicate them somehow. I just decided to give them a number from 0 to 3 in the order of how we implemented them. So 0 corresponds to the one that takes the integers directly, 1 with CC nodes, 2 was truth table, and 3 the last one that used this more complicated expression. So I pass in this type argument as an integer. I check that these with an assertion that this type is in the right bounds. Then I create 3 qubits, and I apply one of these operations that I based on the type. And again, like we use this signature to perform the exhaustive verification and passed in an operation type. So this is an array of type majority operations in some sense. Because they all have the same signature, we can put them in an array. And this is an array of operations now. And I can work with them and deal with them in the same way as if it would be an array of integers, so an array of qubits. I pick the operation that I want, which is based on the type, and then call this operation on the input and output qubit. So I don't want to do anything else with it. I just want to simply call this operation. I don't want to assign the inputs to something. I don't want to read out the value. I don't want to measure it. And I want to use the resource estimator to execute that. And you can take a look here how that would work. So if we compile that, then this is a project that I can execute. So I can do .NET run on the project. It creates also some executable that I can call with .NET. And it takes as input a type, right? This is corresponding to this argument that I passed here. So if I would put more arguments, then I can provide them via the command line. And I can also assign a simulator with this flag -- simulator. And the simulator here is the same as the simulators that I pass in to this test attribute. And they can be like quantum simulator, Toffoli simulator, or resource estimator as an example, or some custom simulator. We will also see that in a bit. So I will provide now a simulator, the resources estimator, and then I have a type. So let's start with the operation that uses integers. And it gives me now a summary. This resource estimator uses this as a gate set, but it could be customized for different architectures. That tells me how many CNOT gates do I need in this operation, how many single qubit Clifford gates, like X, Hadamard, S gate, Y, Z, and so on, how many rotation gates, how many measurement operations, how many T gates, which are non-Clifford gates, and the depths in terms of these T gates and the width. Width is like corresponds to qubit count. And so I need 5 qubits and is 84 T's. So this is a metric that is helpful if we want to estimate quantum algorithms with respect to fault-tolerant quantum computing, like maybe future resource analysis, where this T operation, that's why it's mentioned explicitly here, is typically considered to be a more expensive operation to execute, whereas other operations like Clifford operations or the CNOT operations are easier to execute. That may not always be the case for different architectures. For example, in near-term devices where we don't do error correction, single qubit gates such as CNOT may be more expensive than T-gate, in fact. Right? And we can look at the number of CNOTs and try to minimize that. But for the purpose of this talk now, let's maybe take a look into how many C nodes do we need, how many T's do we need, and what's the qubit count. And I summarize them in this resource estimation slide. So the implementation based on ints uses 120 C nodes, 84 T's, and 5 qubits. Now, if I use a different operation implementation, and now I use the type 1, which is the one using 3 CC NOT gates, or 3 Toffoli gates. Now, this uses, I take these numbers here, it uses 30 C NOT gates and 21 T gates only. So we reduced the number of T gates by about, and the number of C NOT gates by a factor of 4, just by providing an alternative implementation. And also affects the number of qubits. And 1 qubit less is needed to do that. And also depths increase significantly. Where does this 21 come from? Like the number of top T gates to produce a CC NOT gate is, in its standard way, it's 7. Now the next operation, what was the operation that uses the truth table? So it has this operation, library operation, applies control and truth table. So we didn't really do, in some sense, we didn't try to find some specific representation, and let's say in some say do anything smart. We just use the operation, we explicitly specify truth table and see what happens. And if we call that, then we get these numbers, and maybe easier to compare with the others, which uses 14 C nots. So another factor of 2 improvement over C NOT gates, and 8 T gates, which is another factor of 3 to improve on the previous implementation, and uses 4 qubits. And finally, the last implementation, which maybe was like the hardest to find. Maybe you have to do this Boolean expression manipulation. And that one improves further, not on the number of C nodes, so 1 more C node, but we get 1 less T gate. So maybe for fault-tolerant quantum computing, this would be preferred. If you don't have error correction on a noisy device, maybe we want to have the truth table version, which has 1 less C node, could be preferred over there. So it's good to have different implementations. Maybe the last 2 are the ones that are now interesting to keep in our library, and to use them in different situations based on what applications I want to use. So this is, the C node transformation is the one with the expression. And so we could write more implementations, and if you're interested in maybe trying this out and writing your own operations, or like seeing different ways to implement the majority operation, I can just tell you that there is a way to improve this result. If you, for example, are interested in the number of T gates, then it's possible to do this with 4 T gates. And I leave it up to you if you're interested to try to find this better implementation of the majority operation. All right, so now we have basically done our verification. We have implemented our library. We have checked that these operations are in fact implementing the operation that we want to do and compared them with each other. We performed resource estimation to get understanding what are the good operations, the good implementations, and which one are more expensive. And now we want to maybe like understand a bit why is this? So how come? Because we see this high level code here, but for some of them we see kind of what's going on a bit more in detail. But for some of them we have like operations, like library operations, which is nice for us in the code to see, to have like a clear code that expresses what we're doing. But we maybe want to understand a bit better what's going on under the hood, and why do we get these resource estimates that we got. And for this purpose, I'm going to use a custom simulator, and you find them in the quantum samples repository from GitHub repository from Microsoft. And this is also described in the Q# blog. So I have another project here which I took from the, so I copied this over from the Microsoft Quantum Samples repository. And this is implementing a custom simulator. And I don't want to go into detail about how these simulators are implemented in this talk, but just to show how you can use it. But essentially, it is a C# implementation of some interface that then, as I mentioned, I mean, I can go a bit here, that has like specific operations for each of the possible elementary quantum operations that I can do. Right? Well, what happens if I call a Z gate? What happens if I call Hadamard operation? What happens if I call a T operation? And then I can fill these procedures with my own custom code. And what I'm doing here is I create what is called QPIC, which is a syntax for describing quantum circuits. Now, Q# programs are not the same as quantum circuits. Q# programs are on a high level of abstraction to express control flow and quantum computation. However, the execution of a Q# program can be represented using a quantum circuit. The quantum circuit is representing the trace of the execution. A Q# program may go different paths depending on the control logic, but I can capture the execution of this program inside a quantum circuit. And now, instead of like writing down the operations that I encounter, I try to align them in some kind of diagram visualization, and I can use the quantum circuit to do that. So I'm taking my test project and linking this simulator to there by including it into this test project as a reference. And then, exactly as how I use these the simulators that are shipped with the quantum development kit, like Quantum Simulator and Toffoli Simulator, I can also use my custom simulator by addressing it with a concrete full namespace and class name that it's defined in. So this, for example, is in namespace Microsoft Quantum Samples QPIC Simulator. And that's why I give the fully qualified name. And then it will run this code using the simulator. So here, similarly, like in the first test where I'm calling this verify majority operation, I created a generic visualize majority operation that takes as input also one of these operations that implements the majority function, and as another argument, a file name in which we want to write down the visualization. So how is this implemented? This is a bit shorter. It creates 3 qubits, calls the operation, and this is wrapped in this safe picture operation. The safe picture operation is an operation that is shipped together with a simulator. So this simulator defines its own operations, for example, safe picture, that do nothing. So they are not implemented. That means that if you call them with any other simulator, nothing will happen. They behave as no operation, but they are implemented in terms of the simulator itself. So I said I don't want to go into detail, but for the specific simulator, these operations are implemented. But it's safe to use them with other operations, just don't do anything. So we can write them into our code. And here we used kind of like this paradigm of wrapping within apply to scope which part of the code I want to save as a picture. So I use this within apply. So essentially, if I call save picture in the forward direction, it says it starts recording operations to be part of the visualization. And if I call adjoint save picture, it stops recording this operation and writes all the operation it has recorded so far into the file name. And then I can wrap it with an apply to kind of like make it look like this. So these, while I executed the test, these files were generated. But if I would have them in executable, they would be in the same folder. But because it's in the test, they end up in the in this output folder created by .NET, what is written by execution. I could have maybe also given a complete pass to write them somewhere else. So they ended up being here. And then they have these QPic syntax that is a way to describe these diagrams. So then there's a QPic command that can, for example, you can pass in a format, PDF or TeX or PNG, and give a QPic file name and generate these files, and they have been generated here. And now we can take a look at these generated files. So this is the file for the first implementation. It uses integers and essentially really creates fully controlled NOT gates on all the inputs, and it takes a positive control and for positive values and negative control for negative bits. So this gate together with these two X's is like a 3. So I think the order of qubits would be like, here's the x1, x2, x3, that would be 0, 1, 1. And this would be a 5, right? This is this X inverts this control line, so it would be like something like 1, 0, 1. This would be maybe 0, 1, 1, which is a 6. And this is a 7, like 1, 1, 1. So it really creates fully controlled gates for each of these 4 integers that I have passed, and then executes them. And then they have to be, we didn't see the number of 3 controlled qubit gates. We didn't see the number of 2 controlled X gates. They are like internally decomposed into smaller operations, and then they are counted. And it's kind of like expensive to break them down into small operations. The second implementation that uses CC0 is smaller now. Right? It uses explicitly these 3 CC0 gates on these qubits, so we can immediately recognize our operation. That we could have seen also in our code, as it directly calls these intrinsic operations. And the two-step operation, this is a bit more interesting. So it creates this larger circuit using CNOT gates and rotation gates. And if we, so without going too much into detail, but there are a lot of operation gates, but some of these operation gates actually have a 0 angle, so they're like identity gates. And if we count the one with a non-zero angle, like these 3, there's 4, 5, 6, 7, 8, then and the angle will be in a way that they correspond to a T gate, then we have like 8 T gates, and that's where the 8 T gates are coming from. And I refer to the QSharp documentation of this operation. Which is over here, which has a reference to the literature, which describes this kind of construction. Why this works and why this is universal for any kind of truth table Boolean function. And finally, the one from the expression is also something that we can kind of like see from the code. We have these 2 CNOT operations in the beginning, then the CC0 on the CNOT on the target, and then the inverse operation. Right? We have in the code, we see this with an apply, but as said, this is just like taking the within block afterwards, inverting it, and executing them in reverse order, which is exactly happening over here. And this now, from this, we can kind of see with the knowledge of like, okay, a Toffoli gate requires 7 T's, and these are all only CNOT gates, and we can kind of understand where the cost is coming from. Well, and that's kind of it. Let me just summarize by going back to the beginning and showing this picture again. And this is exactly what we did. So we have an algorithm, and now our algorithm was simple. We just want to implement the majority operation, but potentially it's much more complicated. But the flow stays the same. we implement this algorithm. We may optimize it either like manually, like writing different operations, or rewriting the program using using rewrite steps. So like I didn't touch it, but like also similarly as you can write your own simulators, you can write transformation passes on the Q-sharp program. Like you can access the abstract syntax tree and then changes and also like extend the environment by these tasks, which is more advanced, of course, but like it can also further help you to optimize resources by not changing the program. And then different tests on different tasks can be performed. Like we did verification to check if the function is correct, comparing different implementations, resource estimation to see what is the preferred operation that we want to use maybe, and to understand what is the difference between them qualitative wise, and visualization for the diagnosis. And this cubic diagrams is one way, but maybe there are other ways to visualize something. If the operation goes more complex, then quantum circuits may not be scalable for that, but then maybe we have other visualizations that we can envision to do that. One example maybe for like large programs, in the last Q-sharp advent calendar, one external contributor made what is called a flame graph. A flame graph is like visualizing the call stack and emphasizing where a call stack like maybe requires a lot of operations and where just a few. And you can kind of like have a quick overview on like basically where is this burning. That's like a flame graph, like where do I spend a lot of operations, and then use that as diagnosis for your algorithm and see where you could improve your code. So the takeaway, yeah, you can write everything in one framework, and it's very extensible with respect to writing your own simulators or simulation passes, using the same language to the testing, doing everything in this kind of like controlled flow. And a lot of functionality is provided already inside the QDK using, for example, standard libraries. And I invite you to take a look to see what's in there, maybe to take this example and write your own operations, see if you can improve them further. Probably you can, and then probably they're improvable. So I would like to see that. And yeah, now leave the floor to questions. Thank you.
Thank you, Mathias. Thank you so much for the great and detailed overview of test capabilities and capabilities to run the simulation of the program execution before running on the quantum hardware, and also resource estimation. That was, I think it's very, very useful topic. And with this, I invite everyone in audience to ask questions now and see if you'd like to hear more details from Mathias. So I'm looking at our chats both and in Zoom and YouTube, so you can type your questions in either chats you prefer. It looks like so far everything looks great. There are no questions. Maybe while maybe we're waiting for questions, Mathias, you could remind for those who would like to learn more in details and grab some more insights in what you presented. Maybe you could remind the resources they could go to and get more information.
Definitely. So I think this is so the Q-sharp blog is also a good resource to see what there is. Like it describes a lot of like advanced functionality or like things, use cases that you can do with the QDK, and it has a lot of interesting. I found like Advent Calendar, for example, very interesting. Very like a lot of different applications also from the community, and what they did. We do this every year, and every day there's a blog post about something, what's going on, and specifically for the talk today. And there's a series of build your own Q-sharp simulator, which like addresses the last part that I had of like how to write your own simulator, and then there is the cubic simulator described over here. The documentation is a good entry point. It's not only this API documentation, right? It has all these getting started guides. You can pick how you want to implement with a Q#. Sorry, how you want to implement Q#. It has guides for how to implement using VS Code, VS, .NET. You can also call Q# from Python, right? How would that work? And pick kind of like your favorite entry point where you're most comfortable with. So for me, it's like .NET and VS Code, but like if it's Jupyter Notebook or Python, then that may be the way to go. And this has entry points on how to go with that, but also like concept into quantum computing. Right? Like, is it some basic on quantum computing is needed all here, and links to the QDK. And I guess yesterday Maria has mentioned the quantum katas, which is an excellent starting point for learning both quantum computing and Q# concepts. So that is like for just getting like familiar with the language, quantum computing concepts. And I think for trying that out, it's perfect, and the notebooks are perfect. And then for big projects, you can also then scale it, for example, with .NET projects and VS Code.
Great, thank you so much. We have another question. It might be slightly off topic, but I think still interesting for the audience. Does Microsoft offer some sort of certification for Q# developers?
I don't know that, but I'm happy to get back with the answer to that question and ask inside the team if there's something available.
Yeah, great, thank you.
I can't answer right now, but like if this question, like please feel free also to look me up and try to find my email address or like my LinkedIn or something like this, and just reach out to me. I'm happy to answer questions also after this talk.
Right, great. I don't see any other questions. So with this, I would like to thank you, Mathias, again for presenting at the QSC Quantum Summer School. It was a great pleasure to have you, and I hope they'll see you also for our future events. Thank you so much for joining us today.
Thank you for the opportunity, and thanks for organizing this event. Thank you very much.
Thank you. And with this, I would like to conclude our morning session. We will have 1 hour break now, and then we'll resume with lectures. Just a small announcement that the next lecture that will start at 12:30 will be available only for registered participants who have a Zoom link, and this lecture will not be streamed on YouTube, but the YouTube live stream will resume at 1:30 p.m. with next 2 lectures and panel discussions that will involve speakers from today's session and also from the previous days. So with this, thank you so much for joining the morning session. We will have a break and see you in the afternoon. Thank you so much.